Alright kids, today, yes, it's for Monday. The Monday you come back, you got a candy hangover. I know it's going to happen, right? On Monday, I wasn't going to tell you either, so consider this a little present. I know, that is. I know. I can't keep a secret. Alright, so what you'll have to do, you're going to have to sketch, yes. You're going to have to sketch a little slope field. So I'm going to give you a differential equation. The derivative equals whatever, okay? It's going to be a nice one. You're going to sketch a little slope field at whatever points I indicate. Then I'll tell you a point that the solution has to pass through so you can kind of draw in what the solution looks like. Okay, try to follow the lines. And then comes the best part. You actually get to separate and integrate and solve it. And then hopefully, if you get, let's say, y equals x squared plus 3 as an answer, when you separate and integrate, your solution looks like the graph of y equals x squared plus 3. But something's wrong. So it's a little way to check if you did the first part right, or something to look forward to. We're going to start out by solving one of these, similar to one of them that was on the homework last night. Not quite the same. I want you to actually solve this differential equation. So remember the basic steps? Separate, integrate, solve for C. Bam! Go ahead. We'll see how many people get it right. I didn't check yours, did I just? Do you have it? Okay. All right, guys. Let's go ahead. Anyone think that they have a solution? All right, Gina. What'd you get? You agree? Oh, and that's going to be right, I think. Yeah, let's first of all, let's see if you separated correctly. Alright, so let's make sure that on one side you have dy over y minus 1, and on the other side you have the x squared dx. Any question on that part? Sure? Okay. Guys, back there, you separate? Did you separate correctly? Alright. Now you have to integrate. Now on this side, this is like a du over u. Do you see that? This is, so if anytime you have to go integrate a fraction, if the numerator is the derivative of the denominator, you're just going to get the ln of the denominator. So the left side, when you integrate it, is the ln of y minus 1. What about the right side? X to the third over 3. Let's see. Ooh, I gave away the good stuff. So you should have the ln of y minus 1, and don't worry about the absolute values with these, equals 1/3 x cubed plus c. Now, yeah, I already gave it away, so you want to solve for y, you got to get rid of ln, you're going to exponentiate. Now, this is the one part I think we might be getting a little confused on. What's the left side? Y minus 1. But on the right side, since the plus c is up in the exponent, we know we could break it up into a product and all that. Where do we put the c in the next line? Front. So if you move it up front, you don't have to show this line in the middle where you break it up. You don't have to do that. You just want to go to y minus 1 equals c times e to the x cubed over 3. Then you can use that initial condition that at 0, y is equal to 3. You can plug in those values and solve for c. What did you guys get for c? 2. So when you plug a 3 in for the y and a 0 in for the x, remember e to the 0 is 1, you get c equals 2. When you get what c equals, you're not done. You got to go back up to the line before and plug the c in. So you have y minus 1 equals 2 e to the 1/3 x cubed. And then you can just add 1 to both sides. Separate and integrate. That's not the worst thing, right? Oh, good. Okay, so now I have included In your notes, it's the second to last page, the solutions to the homework problems. It's a good thing. It's a good thing. Yeah, I know that there are questions on B. I love B, the first one. That was fun. Talk about that. Yeah, I had some questions on B, so you can ask whatever you want. Let me just see. That first one was 2004B, the first problem. I just wanted to address it because when I was going around the room, some people were asking, and I just think I just wanted to answer that part B. If that one, then we can answer we can go over anything else you want to go over. But in that one, the slope, the derivative, is equal to x to the fourth times y minus 2. And they say, you see a slope field for a few points here, but there are an infinite number of points. Describe the points where the slope is negative. Now, the slope is the derivative. We want to be able to describe all the points where the derivative, the slope, is going to be negative. And if you look at this, it's a product. Can you guys tell me when a product can be negative? Yeah, when one factor is negative and the other factor is positive. Right? So can that first factor, x to the fourth, ever be negative? No. So the only way that this slope, this derivative, can be negative is if the first factor is positive. So this slope is going to be negative if the first factor, since it can't be negative, it's going to have to be positive. And the second factor, the y minus 2, is negative. Does that make sense? The only way a product can be negative in this case is if this factor is positive and that's negative. Okay, tell me about what numbers, if you raise them to the fourth, will give you a positive number. Everything except 0. So x can't be 0, and then x to the fourth will be positive. And for what values of y will y minus 2 be negative? And even so that's what they were looking for there. All the points where the x coordinate's not 0 and the y coordinate's less than 2. It's not bad, right? You see that for the first time, like, whoa. Well, there was some other part B, I think, with a tangent line that also I know somebody was asking. Was it the next one with a tangent line? 2005. I love that one. I want to go over that one. Just extend. In 2005, can you remind me what the derivative was equal to? Negative 2x over y. And in part B, they wanted you to write the equation of the tangent line. At what point? 1, negative 1. They want us to write the equation of the tangent at 1, negative 1. So they already gave me my x1 and my y1. We want to write the equation of a tangent line. What's the only other thing we need? The slope. So you see, we already know our x1 and our y1. So far we know it's y plus or minus. Yeah, because it's minus negative, so plus 1. So once we can figure out the slope, we put it there and we're done for writing the equation of the tangent. How are we going to get the slope? That's right. Yeah, the differential equation is a formula to get the slope. Y dx, that just means slope. So at that point, 1, negative 1, it's going to be negative 2 times 1 over negative 1. 2. So here's the equation of the tangent line to this function at that point. And did we have to use it to approximate something? 1.1. So if you have to approximate the function at 1.1, you don't plug 1.1 into the function to x of the function because you don't know what it is. What do you plug it into? Tangent line, the x of your tangent line. So I would subtract the 1. So let me see. So y equals 2 times x minus 1 minus 1. That's the tangent line. The y is on the tangent pretty close. So we just say f of 1.1 is approximately equal to, and you plug 1.1 into that. You never want to distribute those tangent lines because it's always easier. Because you have 1.1 minus 1. What's that? 0.1, and then you multiply it by 2. 0.2. 0.2 minus 1, negative 0.8. Okay. Yeah, so look to see if you got your slope fields right, and I'm especially more concerned about the first two because it's a more basic problems. Slope fields right, and your solution if you separated and integrated. See your mistakes. Questions? All right, well then today we're going to have some more fun with differential equations. We're going to keep going. All right? What's that? Oh no, I wanted you to, but it was just it was tougher. The last one you're talking about, 2006. Do you have questions on it? The separating and integrating. Okay, can you just take a look what I have because or else I'm not going to get to my whole lesson. It takes a u sub on both sides. Like which side did you have more trouble with? The right? With the pi x, the sine of pi x, I think. Yeah, if you want to integrate the sine of pi x, u is your pi x, so you need a pi. You have to put a pi in there and a 1 over pi on the outside. See? Yes. Yeah. On the AP exam, they would take that. That's not, but yeah, that's fine. All right. Well, today we're going to talk about one particular differential equation. One special one. No, no, this is not ugly. You're actually going to think it's beautiful by the time we're done. If you have a situation, like a population, okay, if there were no diseases and there was unlimited food, so there was nothing to stop a population from growing, isn't it true that, when you only have a few people, the rate of increase of the population is pretty small, right? But then, as the population gets going, let's say it's growing at a rate of like 3%, now in a year, think about the change in the population. It's much greater, right? Whenever you have a situation where the rate of change, okay, so you start out with some amount, but the rate of change is like the slope, is proportional to the amount present. That means it's just like 1% of the amount present. You can see that your graph is going to start shooting up. It's going to look like this. You start out at some amount, right, whatever the initial amount is, and the slope, it's going to get steeper and steeper. If the slope is always like 1% of the y value, it's going to get steeper and steeper. And there are things that occur, like, if you have like bacteria and there's nothing really to stop them from growing, they might grow like that. This is known as exponential growth. But, a lot of cases, you're going to run out of food and it won't just keep growing like that, unlimited. But we're going to talk about this one differential equation. We're going to solve it. And here's the good news. Once we separate and integrate and get a solution, you just have to know the solution. You're just going to memorize it. You can use it. You don't have to do it every time. Who's up for that? Yeah. Oh, yeah. And so we're going to go ahead. Now, the one thing, though, before we start, sometimes they're not going to say, hey, here's the differential equation. So sometimes they're just going to give you some words, and you have to realize it's this. So I just want to kind of translate this. So if you see it in words, you know it's the same thing. Let's say I have some quantity y and it's changing. If you talk about the rate of change in your quantity, that's just dy dt. If your quantity is y, you can call it anything you want. dp dt, change in population, be change in time. But the rate at which anything changes is d that dt. So when you have a population or a quantity y that changes, and the rate of change, dy dt, is, the word is, mathematically we use equals proportional to. Proportional to just means like 3% of or 2% of. It's just some number times. So whenever you see proportional to, oh, I use the same color. Shoot. Sorry, I'm going to use a different color for each one. Okay. It is proportional. No! I'm just going to give up. It's proportional to, you always write when you have a word problem, k times. Every time you see the words proportional to, just say k times. K is just a constant. It's usually like 0.01. It could be negative if it's decreasing. And then the amount present is just your y. If I'm calling my quantity y. So sometimes they'll say dy dt equals k times y, but sometimes they'll say that quantity y is increasing at a rate that's proportional to the amount present. And you have to realize, oh, that's the same thing. Alright, let's get the solution to it. You're going to love this. It's easier than what you've been doing. So, we have this quantity y. It's growing at a rate that's proportional to the amount present. And we're going to say that at time 0, y equals y sub 0. That's going to be my initial condition. Sometimes in your science classes you use y sub I for the initial quantity. We use sub 0, like y at time 0. Okay. So, first thing we have to do to solve this, we're going to separate the variables. Now, the variables are not y and x. What are the variables this time? K is a constant, not a variable. It doesn't change. It's y and t. So let's get the y's on one side and the t's on the other. How come you're not separating? Guys, separate. It's multiplication, division. You know, you might want to write it like this. Okay, so if you get the y's on the left, what is the left side? dy over y. Okay? K times dt. K technically could be on either side, but when you're trying to solve for y, you want to keep the y side as clean as possible. So any numbers you just put on the independent variable side. Okay, we separated. Integrate. dy over y, we integrate that. Ln of y. Now, k is a number, okay? And the variable is t. So what is the antiderivative of k with respect to t? kt. And then what else do we have to remember on this side? Nice. Good. Now what? I don't like to solve for c with ln's until after I exponentiate. I don't know. Maybe it's me, but technically you could find it any time, but then it's a mess. Don't you dare use that language in here. Okay, exponentiate. E to this side equals e to that side. I hope you remember what to do with that plus c up in the exponent. Come on down. Yes, we have y equals, and that plus c, we could break it up and show all the work, but where do we put the c? In front. So it's c times e to the kt. Now we'll figure out what c is with the initial condition. So remember they said at time 0, your quantity was your initial. I know it's kind of like you're saying the obvious, but when t equals 0, y equals y at time 0. It's your initial amount. E to the k times 0. 1. So C is just y0. Now, whenever you find C, you go back to the line before you plugged it in, right? And you put that value in. So our solution is going to be y equals C we just found out is y sub 0 e to the kt. This is the law. It's the law, people. It's the law of exponential change. And you're allowed to use this solution whenever you're told dy dt is equal to k times y or in words. So, does that look familiar to you? What does it remind you of? Trig? Okay, what formula did you ever use that looked like that? Hertz! You said a part? Do you remember, guys, if you want to find the amount of money at time t, what did it equal? The amount of money at time t you invested, and the interest is compounded continuously. P, that was your initial amount of money, your principal. Why? Maybe some people didn't do it, I don't know. But it's your principal. Well, think of this. You go to the bank, you invest, let's say you have $100. That's your principal. It's your starting money, okay? Maybe you're a little overly sensitive then. Then we said E, we didn't use K for the constant, we used R, because it might, it made more sense actually. Because it was like, if it was 1% we were making on our money, it's R, yeah. And then T. So if you invested your money, $100, and you were getting a rate of interest at 2%, and you want to find out how much money you'd have after 50 years, you'd plug in the 50 into the T, 0.02 into the R, and your 100 here, and you just pop it in the calculator and you could figure out how much money you had, right, after 50 years. This is this. We just derived this. Oh yeah, that'll mess things up. Yeah, it was. Well, the worst thing I would say, you could say, how much time will it take to invest about $100 equal $200? You solve for T. That's the formula. You just know it like this. You see how it's the same thing? Okay. Yeah, it's just that realize it doesn't have to be money that's growing or decaying. It can be anything. In fact, it could be bacteria. It could be population, it could be bacteria. Radioactive decay, carbon-14. It decays at a rate that's proportional to the amount present. And guys, I just got to show you something that's the coolest thing before I even do this problem. Guys, with this, whenever you have this, whenever the rate of change is proportional to the amount present, if the amount is growing, if K is positive, your money or whatever is going to be going like this, right? If it's radioactive decay, if a quantity decreases at a rate that's proportional to the amount present, you start out at y0 and it decreases. But here's the coolest thing. I got to tell you about this exponential growth. No, don't. You guys are tuning me out. I'm going to show you that in a second. Okay, well, ln of a half is just negative ln of 2. Because it's ln of 1 minus ln of 2 and ln of 1 is 0. Okay, but guys, here is the neatest thing. It takes the same amount of time for your money to go from $1 to $2 as it does to change from $1,000 to $2,000. When you have the law of exponential change, it doesn't matter how much you start with. It always takes the same amount of time to double. Just like with radioactive decay, when when K is negative, it takes the same amount of time for 1 gram to decay to a half a gram as it does for 1,000 grams to decay to 500 grams. That's the neat thing about this. It's always proportional to the amount present. Now, I did put this on here because when I put the derivation of it on your sheet, they're good little nice little formulas to to know, because they're almost the exact same. The half-life is just negative ln of 2 over k, and I wrote it on your paper, and doubling time is positive ln of 2 over k. Time it takes to double. All right, but let's actually try a problem so you get a feel for it. No, it wasn't. No. All right, let's see how this can help you in your life. So you have a culture of bacteria, and it grows so that the rate of change of the population is proportional to the population. We're allowed to use it. Once you see those words, bam, you're allowed to use the law of exponential change. That's your permission right there. Suppose the population was originally 100. So that's your Y0. And 2 days later, the population is 100,000. That's what you're going to use to find your K. Sweet. So actually, let's do that first. So I'm using this first little bit of information. When T equals 2, the population is 100,000 to solve for K. So we're going to put well, we're going to use this formula. We don't have to separate, integrate. We're allowed to use it because of these words up here. Y0 was what? 100? E to the k times 2, or 2k. How do you solve for k? Divide by 100? Yeah. Yeah, you can't ln first. Because if you have the ln of a product, you're going to have to take the sum of the logs over here. Yowza. You don't want that. You got to get rid of that 100 first. So divide by 100. So you had 100,000. Divide that by 100. You have 1,000. Now, what can you do? Yeah. So the ln of 1,000 is equal to 2k. Divide by 2. So now we know what k equals. And you know, whenever you solve for k, or whatever you want to call it, something an exponent, don't round that thing too much. That's going to throw off your answer. I'm going to leave it like that. All right, now let's see what they want to know. How many days does it take for the population to reach 10 to the 11th? How many days does it take? What are we looking for? Time. So we're trying to find the time it takes for y, the population equal 10 to the 11th. That's a lot of bacteria. I hope it takes a real long time. So 10 to the 11th, y0 is still 100. E, now we know what k is, and we can solve for t. K is the ln of 1,000 over 2, and then we want to solve for t. We did. Divide by 100. If you have 10 to the 11th and you divide by 100, what do you have? 10 to the 9th. We subtract exponents. So now we have e to the ln of 1,000 over 2 times t. Now what? Ln now. So the ln of 10 to the 9th equals the ln of 1,000 over 2 times t. Is it good to get back to math, like fun solving equations? Now we want to get t by itself. We can divide by the fraction or multiply by its reciprocal. I like multiplying by reciprocals. So if I multiply each side by 2 over the ln of 1,000, so by 2 over the ln of 1,000, have the t. We don't need a calculator for this. You don't believe me, do you? So you don't believe me that we don't need a calculator? No, don't trust me. I will lie to you. Does anyone see anything I can do here so I don't need a calculator? Well, no, because it's not the This we can make 10 cubed, okay? In fact, I'm just going to write it as 10 cubed. When you have a log of something to an exponent, where can that the exponent can come on down? Let's write this as 2 over, if we bring the exponent down, 3 ln of 10. And then up here we've got 9 ln of 10. Oh, you did on the calculator? It is 6. Because now you can cancel. So you have 18 over 3, or you have 6. And kids, in 6 days, you're going to have 10 to the 11th bacteria. Yeah. T is measured in time. Because every population, every substance has its own value of K. And before you can, it's the rate at which it's going to be changing. Yeah. Like your bacteria is changing at a rate, whatever that is, think of it as a percent of how much present, the amount present you have. Everything. You have to solve for K first. Wait, let's do this. Let's do the summary. I don't get to do any of the radioactive decay, which is fun, but all right. How do you know what conditions have to be met so you can use this law of exponential change in equation form? Like, what's the differential equation you have to be given? D. We can use y or p or whatever you want, but dy over dt equals to k has to be proportional to y, the amount present. Now, you might be given, it might be a p instead of a y. They might actually put the number in here, you know, but you have to recognize if you have that, you can use it. What about in words? The rate of change is proportional to, I just typed it really fast before because my handwriting is pretty bad. Okay, yeah. Whenever you see the words, the rate of change is proportional to the amount present. Not proportional to the amount present plus 2. No, can't use it then. And just proportional to the amount present, you can use it. Then you have to separate and integrate from scratch. This is just the ready-made solution that you can use. And what is the law of exponential change? Right. Now, this, you should look, it's actually cool. And whenever you have a quantity that's increasing, the time it takes to double will always be the ln of 2 over k. This is a good thing to know. It could save you a lot of time. And the half-life, the time it takes for a quantity that's decreasing a half, will be negative ln of 2 over k. That'll always be the amount of time. So if you know what K is, like we knew for the bacteria, and we wanted to know how long it's going to take for the bacteria to double, we would just take ln of 2 over, remember we had ln of 1,000 over 2? That number would be how many years it takes, or days, I think it was days in that problem, to double. Guys, your homework is there's some just word problems. You get to use this law on all the word problems. So K is negative when your quantity is decreasing. So K is going to be negative. That's why you get positive time. You always get positive time. Yeah, when you have a quantity that's decreasing, K is negative.